Welcome to Thermodynamics. Thermodynamics is the study of energy transfers in chemical reactions or just in physical changes like maybe a phase change. So there's a few vocabulary words that we should get straight, and sometimes the words heat and temperature are used interchangeably, and they probably shouldn't be. Heat energy refers to the total amount of kinetic energy associated with the motion of particles. Those particles could be atoms or molecules, just depends on our particular substance. Now, a few things that we should pick out from this definition. Number one, we're looking at kinetic energy. And kinetic energy is energy of motion. So we're looking at how fast the particles are moving. If particles have more kinetic energy, they're moving faster. If they have less kinetic energy, the particles are moving slower. So heat energy measures the total amount of kinetic energy associated with a group of particles. Okay, so now when referring to total kinetic energy, heat depends on quantity. It's an extensive property. It depends on the quantity. So anytime we calculate the amount of energy gained or lost by a particular sample of particles, we're going to need to know the quantity. We're going to need to know our sample size, and that could be given to us in grams, it could be mass, or it could be your old pal, the mole. If I were given moles of a substance, that represents a quantity of atoms or molecules. Heat depends on total quantity. And then we'll get a measure of total kinetic energy. Temperature measures average kinetic energy associated with a sample of particles. If we're measuring average kinetic energy, temperature is an intensive property. It's independent of quantity. It doesn't matter your sample size, you'll get the same average kinetic energy or average temperature. So here's kind of an example. Here's how I keep the two straight. Let's say you have a giant bathtub and it's full of warm water. And warm water may be like 35 degrees Celsius. We're so used to measuring in Fahrenheit. So let's say I have water at 35 degrees Celsius in a giant bathtub. It's warm water. Then I take a small cup. I take a small sample of water from the bathtub. I immediately insert a thermometer into the bathtub and the small cup of bath water. And they may read the same temperature. They're both at 35 degrees. Because on average, the particles have about the same amount of kinetic energy. They give me the same temperature. Okay, but now let's say I add ice cubes. I'm going to add ice cubes to the giant bathtub full of warm water, and I'm going to add ice cubes to the small cup of warm water. And I ask myself, which sample should melt more ice cubes? The small cup of bath water or the large tub of bath water? And again, they're both at the same temperature. And we're going to try something like this in class, and we should find that the larger tub will eventually melt more ice cubes. I don't know, maybe the small cup could melt 1 or 2 ice cubes. It is warm water. But the larger sample, the large tub full of warm water, will eventually melt lots of ice cubes because there's more total heat energy. There's more particles. There's a larger quantity in the bathtub. So the more particles, the more total heat energy. And I can kind of prove that by trying to melt ice cubes. Kind of the same thing, like I could have water boiling at 100 degrees. I could have 10 milliliters of boiling water. I could have a very small sample of boiling water, and the water should boil at 100 degrees Celsius. Then I could have maybe a liter. I could have 1,000 milliliters of boiling water, and it's the same temperature. They both boil at 100 degrees. Any sample of water boils at 100 degrees. It's an intensive property. Temperature is independent of quantity. On average, the particles have the same amount of average kinetic energy. However, again, let's say I try to add ice cubes. The small sample of water might be able to melt a few ice cubes, but a larger sample of boiling water contains a lot more heat energy. There's more particles. So eventually, I'll be able to melt more ice cubes in a larger sample. There's more total heat energy. Now, we'll use this concept of heat and temperature in a few ways throughout this unit. We'll look at specifically energy transfers associated with phase changes, which are physical changes. And then toward the end of the unit, we'll look at chemical changes. And we kind of know that, that's one of the requirements of a chemical reaction. There should be an energy change, whether it's endothermic or exothermic. The first half of this unit, we'll really just look at phase changes. So no chemical changes, no synthesis, decomposition, replacements, none of that stuff for a little while yet. So these terms should be familiar to you. A few more vocabulary terms associated with phase changes. We can look at phase changes in an endothermic direction or an exothermic direction. So let's say I start with an ice cube. I start with solid water. If I add heat energy in an endothermic direction, I would melt the ice and turn the liquid or solid into a liquid. So melting is an endothermic phase change. Endothermic meaning I would have to add energy. I'm increasing the kinetic energy of the particles, which is another thing that we'll look at in class. We'll look at a couple ways that we can demonstrate this. But in the solid phase, the particles are packed real tight. There's not a lot of movement. There's not a lot of kinetic energy. But as I add energy, the particles should move around more. I'll eventually change phase. If I keep adding energy in the endothermic direction, I can evaporate the liquid, turn the liquid into a gas, where the gas particles obviously have even more kinetic energy. Now the terms evaporation and boiling both refer to the change from a liquid to a gas. Here's the difference. Evaporation occurs on the surface. So if I have like a puddle of water, it just rained, there's a puddle of water outside. The energy source is the sun, and the sun would be affecting the particles on the surface of the puddle. So if your energy source is like on top of the liquid, the surface particles get the energy first and turn from a liquid to a gas. That's evaporation. It occurs on the surface of the liquid. Boiling occurs from within, where your energy source is on the bottom. So if I have a beaker of water on a hot plate, the energy source is on the bottom of the beaker. So it's those inner particles on the bottom of my liquid sample that absorb the energy first. And so that's why we see the little bubbles in boiling water. As the liquid turns into a gas, the gas is less dense than the surrounding liquid, so those gas bubbles will eventually rise to the surface. So they're both the change from a liquid to a gas. The difference is just where the energy source lies. Evaporation, the energy source is on top, so it's the surface particles that are turning into a gas. In boiling, the energy source is on the bottom. So it's those inner particles that are first turning into a gas. Cool. Now, there's one other endothermic change that is listed on this chart, and it's another one that we're going to look at in class too. Sublimation. Sublimation is the change from a solid directly to a gas. It is endothermic. One of the best examples of a substance that sublimes is dry ice. And we will look at dry ice in class, where just the amount of energy in the surrounding air is enough to change the particles of solid carbon dioxide directly to a gas. Skips the liquid phase. It is an endothermic change. The particles have more kinetic energy in the gas phase. Now we can also reverse these processes, and we can do these changes in an exothermic direction. So if I have a gas and I remove energy, one of the ways we can remove energy is by cooling the gas. The first change that we might see is condensation. This is exothermic. Exothermic meaning that energy has to be removed. When the gas condenses to a liquid, in the liquid phase, the particles have less kinetic energy. We're removing energy from the gas particles. If I continue to remove energy from the liquid, we can freeze the liquid particles back down to a solid. So freezing is an exothermic change. Now sometimes people get this confused because they'll say, but when we were doing all those chemical reactions, if something was an exothermic reaction, it felt hot. The beaker felt hot to the touch. But when I freeze something, it feels cold. And so they get a little confused here. Like ice is cold. Well, in a chemical reaction, you were feeling the energy released. So it felt warm to the touch. Here, when you feel an ice cube, it's, yes, cold to the touch because it's got less energy than the particles did in the liquid phase. The energy has been removed, and often it's just removed to the surroundings, to the surrounding air. And so, yeah, like an ice cube feels cold because it has less energy than the particles did in the liquid phase. Now, the other exothermic change that we should mention is deposition. It's the opposite of sublimation. If you have particles that can go from a gas straight to a solid, we call it deposition. And yes, the particles in the solid phase would have less energy than the gas phase, so energy was removed. If energy was removed or released, the change is exothermic. If I need to add energy, the change is endothermic. And in the next couple videos, we'll get into more detail on exactly what's happening when we do these phase changes.